Okay, so this is the presentation for abstract varying representation by Minxin Huang and Nadia Ruz. In this presentation, we're going to talk about three main parts. The first part is what is abstract varying representation. The second part is some examples of abstract varying representation. And the third part is the value or contribution. Okay, let me begin by explaining abstract varying representation. Abstract varying representation is when there is a family of representations with a constant core of intrinsic mathematics, but where each representation in the family aims at a different kind of physical system. Basically, what we're trying to do with abstract varying representation is to find the core mathematic structure of a family of physical systems. And we extend the core mathematical structure to more members of the family. Result from varying the interpretation of a given mathematical scientific representation. When different variations are considered, more or less extensive families of more or less related target system arises. Abstract varying representation focuses on the overlapping of mathematics of different members of a family of a scientific representation family. It yields many benefits in the study of scientific. The first contribution of math in abstract varying representation is that it confirms the mathematical link among the members of the family. Therefore, it helps to confirm all members of the family. Once the mathematical link is formed among members of the same family, we could boast confidence of confirmation of one member by experimenting on another member of the family. Some members are easier to test it on than others. For instance, it is easier to conduct experiments on fluid mechanics than on electrostatics. The second benefit of math is that it helps to discover new accurate representations. By varying the components of the mathematics sharing the same family, we could discover new models or systems of representations that we would otherwise overlook. Basically, it could help to develop a toolkit of mathematics that is useful in future study of scientific representations. Abstract varying representation and abstract A-varying representation. Abstract A-varying representation focuses on the A-causal representations in their own right. It focuses on the structure of a given representation deprived of its causal content. It could thus shed light on a mode otherwise be overlooked. Abstract varying representation focuses on the relationship, the overlapping mathematics of members of the same representation family. The success is due to the mathematical similarity between different members of the same family. Easy example of abstract varying representation is the linear harmonic oscillator model. The linear harmonic oscillator model is classic mechanics. It is a system that, when displaced from its equilibrium position, experiences a restoring force proportional to the displacement x. In the linear harmonic oscillator model, f equals negative kx is the mathematics in the representation. F represents the restoring force, and x is a variable represents the distance from equilibrium. In this simple model of representation, there are two members. One of them is metal spring, and the other one is the pendulums. Even though metal springs and pendulums are different in many ways, they belong to the same family of physical representations because they share the similarity in mathematics. That is, they both satisfy the equation f equals to negative kx. Given the equation equals to negative kx, the interpretation of this mathematics varies depending on which exact physical model we're talking about. For example, the materials of the spring might change the components in this mathematical representation. The constant k might change due to the change of the materials of the spring. For instance, a brass spring and a silver spring are going to have different value of k. But even though k varies, the very form of the mathematics holds. By varying the interpretation of k and x, we can confirm the accuracy of a wide range of representations of the same family, including springs of different materials or different models of physical systems that have the same mathematical similarity. Another example of varying interpretation of the same mathematics is to use scalar potentials to represent vector fields. A vector field has both magnitude and direction, for example, velocity and force. Scalar potentials are situations where the difference in potential energy of a vector in two different positions depends only on the position, not the trajectory. Using scalar potentials to represent vector field allows us to move from vectors to scalar, which means individual number. We could use the Laplace equation to interpret systems that share certain mathematical similarities. In the example of e-rotation of fluid, in order for us to fit the system into the mathematical structure, we have to do several idealizations of the fluid. First of all, the fluid has to be incompressible and homogeneous, and we have to make density rho a constant. And second of all, the flow has to be steady. The equation is not time dependent. The third is that we have to ignore the viscosity mu of the fluid. E-rotational instead of rotational. Once we have idealized the fluid in this way that satisfy the Laplace equation, we could come up with some more useful equations for the fluid mechanics. For instance, the Navier-Stokes equations. Also, varying the components of the mathematical models give rise to a variety of systems or physical representations. For instance, by varying the different components of the equation, we could figure out the models that represent a source fluid, a parallel fluid, or fluid flow around an object. Precisely the statics. If we could
Interpretation of one piece of mathematics. The value of varying interpretations. Varying interpretation of one piece of mathematics can be classified according to the following two questions. The first question: how much does the physical interpretation of the same piece of mathematics change? For example, we can use the same math in the same kind of physical systems. In these cases, we just move from one system to other system of the same kind. For instance, from a copper spring to another copper spring. The second type of cases are those where different types of physical systems are associated with the mathematics. For example, in the scalar potential cases, it was represented both velocities of fluids and forces for the electrostatic systems. In the wave charge cases, the math represent the density of cars and the density of fluids. Is the degree to which the intrinsic mathematics of the members of the family of representations is shared. In the case of the harmonic oscillator, which are the springs and the pendulum, the intrinsic mathematics is almost all shared. In the case of irrational fluids and electrostatics, the share is limited. And in the case of the shock waves, which is the traffic jam and the fluid flow, it seems that there's a difference in the basic equations. However, they share a high level property which result in the production of these shock waves. So, someone can argue that due to these differences, variant interpretations do not show scientific benefits. However, according to Pincock, this is false. Pincock says that one of the scientific benefits of variant interpretations is their confirmation power. For instance, mathematical similarities help the confirmation process as follows. If one of the systems shows to have highly experimental confirmations, it seems that this will help to the confirmation of the other system. For instance, let's say that if a scientist believes that Laplace's equation is a successful application for the case of irrational fluids, then this might help the scientist to provide the confirmation of the electrostatic representation. Computer simulation. These have a two-stage transverse confirmation. The first one can be understood as follows. There must be a physical system representation that is well confirmed. Then we can construct a computer simulation that shares the relevant mathematics with our representation of the physical system. Stage 2. We can run the simulation for a new instance of the physical representation. This can generate a prediction. And if this is the case, we can say that we can transfer the conclusion of the simulation to that of the physical system. According to Pincock, the mathematical similarities can contribute to the formulation or discovery of new scientific representations. We can observe two different types of benefits. For example, the direct benefit and the indirect benefit. The direct benefit says that if the members of the family turn out to be accurate, then the mathematical similarities make it easier to confirm the accuracy of the representation. So let's say that a scientist discovers a mathematically link between two representations and turn out to be that one of them is accurate, then it will be easier for him to confirm the other one representation of the other system. And the indirect benefit says that if the reinterpretation turns out to be inaccurate, then scientists can use these mathematical similarities to find out where the failure happened. Pincock this chapter by pointing out the relevance, and I will even say so, the importance of knowing the details of how math is applied. Here, applied mathematics stands for studying the types of mathematical representations and their own right, and how these will help us to understand their implications. For instance, according to Pincock, the understanding of mathematical structures will help a scientist to approach scientific challenges maybe in a new way. As we see, if we understand the abstract representation of Laplace equation, we might come out with new scientific representations. How we approach these new scientific representations. Conclusion. Mathematical similarities shared between two physical systems help to the confirmation of members of the same family of representation. Understanding the applications of such mathematical structures will help you to the discovery, investigate, or develop new scientific representations. The study of applied mathematics helps to illustrate the importance of mathematics in explaining, understanding the physical phenomena.